Hey gang, Math 1500. The title of this video is probably uh, best. I can't I cannot speak and write. It's crazy. Approximating a binomial distribution with using a normal distribution. Sounds glorious, right? All right. So, guys, what essentially I want you to start thinking about here is kind of a switch to categorical variables. But the categorical variable that we're looking at here is dichotomous. And dichotomous just means we have one of two outcomes, hence binomial. Now, but in kind of in the broader study of statistics, what we just did is we looked at normal distributions, and we looked at normal distributions of quantitative variables. For example, IQs, numbers, ACTs, numbers, SATs, numbers. Gestation period would be in days, so therefore numbers. But we're working into something now which is going to be a categorical variable. Hence, it's like a yes or a no, or a true or a false. Again, because we're looking at binomial, where we have one of two outcomes. For example, we'll look at a problem here in a minute. Calculate a probability that a kid is either on drugs or they aren't, a middle school kid. You're either a Kentucky fan or you're not. You're a Ohio State fan or you're not. You're a Republican. Just all sorts of things that we run into in statistics deals with one of two outcomes. Now, a couple of things I want you to think about. First of all, some properties of the binomial distribution. And these are just, let's just call this properties. And just to kind of get you kind of, thinking in terms of binomial responses compared to a quantitative that we've been dealing with here for about the last 3 weeks. First of all, we have what I would call n identical trials. So we have an experiment, if you will, that consists of a fixed number of n trials. Second thing that's important, each trial is independent. So another thing I want you to think about for independence is just that the trials are not related. In other words, picking the second trial has no impact on the third trial. I tell you what you get into a lot if you ever go to Las Vegas or any of the casinos around here, even if you play roulette, you see people that will sit there and they'll watch the colors and they'll say, well, there's been like 7 black in a row, it's time for a red to hit, right? Now, actually probabilistically, what's happened previously, if that spin is truly independent, which we assume it is, or at least they assume it is in gambling, then what happens on that next event is completely independent of where that ball landed on the previous roll. Let's see what else. Okay, each trial has 2 outcomes. We talked about that already. If we were talking about a blackjack, you either got blackjack or you don't. Sounds like I missed Belterra, doesn't it? Haven't been in about 3 weeks, so maybe. Anyway, it could be the ball lands on red or it doesn't. What else do we have? The probability of I don't know how I want it. Let's just call it the probability of a success. That's be a good way to put this. is called P. And the probability of getting a failure is called 1 minus P. Now, success and failure I put in quotations because, you may be interested in the probability that the next child born at a particular hospital is female. So that would be a success and a male would be a failure. Well, you don't mean that a male's a failure. It's just the success is what you are measuring the probability of. For example, what's the probability that the next ball on a roulette wheel lands on red? Well, success is landing on red, failure is not landing on red. Well, not landing on red is not a failure to the person who bet on black. So this whole success-failure thing is kind of in the context of the problem. The random variable, I guess, I'll tell you what, let's go on and get into the parameters here. And I'll do that on the next page. Okay, apparently. All right. On the next page, if the conditions now, if our conditions are met, and guys, our conditions are very simple in these types of problems. All we need is n times p to be greater than or equal to 5, and n times 1 minus p also to be greater than or equal to 5. So if these things are met, then a normal distribution can be used to approximate the binomial distribution. And what we see here, and guys, again, remember, a normal distribution is defined by its center and its spread. Just to, again, to give you an indication, if we've got an axis here, and I'll do something just really quickly, and we say we've got a normal distribution that we want to draw on this thing. Well, if we know the mean, we know that that distribution is centered right there. Well, that's actually, I can't even read my own writing, so let's say 20. And we also need to know the standard deviation to know an indication of spread. So when I know the mean and I know the standard deviation, then I define my normal distribution. So to approximate this binomial distribution by a normal distribution, we have to know what the center and spread are. Well, it turns out the center for this type of distribution is the mean mu, which can be found by taking n times p. The spread of this normal distribution can be described with the standard deviation, and this is given as n times p times 1 minus p. Now, some notation that you see, and I see this in a lot of other textbooks, we can just say that mu is equal to p and sigma is equal to the square root of p times 1 minus p over n. So I will illustrate that to you in a couple of problems, okay? Now, I know right now this stuff seems a little weird when you first start looking at it, but just hang with me, and we'll look at some examples here in just a second, which I think will clear up some of the kind of the vagueness. Now, first thing we run into is when we take a categorical response. And here we're looking at a binomial response. So it's one of two things: true or false, success, failure, this or that. And we try to model this with a normal distribution. Pretend that's an n, which is quantitative. Well, we've got some issues. And the issues are, we have to come in and implement what's called a continuity correction. Now, a continuity correction, all this thing does is it takes a discrete value. And guys, what's meant by discrete? Countable. I can't count your IQ. I can measure it. I can't count your weight. I can measure your weight. I can't count your ACT. I can measure your ACT. But I can count the number of TVs you have. I can count the number of horses that you've ridden in your life. I can count the number of calculators that you have. So when something is countable, we have something that's called a discrete random variable. Well, what we have to do, when we have a discrete distribution like this, we have to implement what's called a continuous, we have to implement what's called a continuity correction to turn this thing into a continuous variable. And it's really easy, and let's just talk a little bit about the notation right now. First of all, P is the population parameter, and this is just the probability of a success. And guys, again, success is relative. N is the number of trials. X is the count out of N that were successes. So what we have to do is we have to take the number of successes, which is discrete, and look at an interval about that by taking x minus a half to x plus a half. So I find out that the probability of winning a particular bet day in, day out is 0.32. I go out in this population and I do 100 trials. I find that of the 100, I had 35 successes. I have to create this interval around 35 by taking minus 0.5 plus 0.5. And my focus becomes on this interval and not the count of x equal 35. Now you're probably sitting there saying, Darbro, you've lost your mind. This is too hard. Well, I'll tell you what, let's work a problem together and see just how hard it is. Okay? I think you're going to find out it's not that hard if you can follow instructions and follow directions, which most of you are doing an awesome job of doing that. So I have this. What is the probability that more than $150 out of 230 eighth graders at a local middle school have been exposed to drugs. Previous studies indicate that 63% of 8th graders have been exposed to drugs. All right, gang. Let's get our notation. What's P? What is the number in this problem that describes the population? Well, this right here. Previous studies indicate that 63% of 8th graders, we're focusing on all 8th graders here. This is just 230 from a local middle school, and 150 out of those 230 say that they have been exposed to drugs. P stands for the statement about the entire population. And again, the entire population here is 8th graders, so we're saying that 63%. Guys, remember, don't ever use a percentage in mathematics. Always convert to a decimal or a fraction. Decimals are easier to work with, so always convert to a decimal. Decimals are easier to work with than fractions. The next thing we want is N. Well, what total number of trials? Well, they chose people one by one all the way up to 230. And then X, in this case, the success. Now here again, success is a relative term. I've seen studies before that are binomial, want to look at the probability that a patient checking into the emergency room doesn't make it, dies, passes away. The success in that particular context is dying in the emergency room. Well, guys, clearly that's not a success in the natural definition of success. But we're not looking at it. We're looking in terms of probability. So again, this problem, the success, is having been exposed to drugs. So we have 150 that were exposed to drugs out of the 230. First thing we have to do here is get the continuity factor. And we call that the continuity correction. And the continuity correction, boys and girls, focuses on the X. It focuses on the smaller number of the total that were sampled. We subtract 0.5. We add 0.5. I had a student one time, I'm going to use a different calculator here in this one. I had a student one time that says, I can't do that in my head. I told her, I said, I don't care. Grab that calculator. So you've got 150 minus 0.5, 149.5. You got 150 plus 0.5. I'd much rather for you to do that than to think that you can do the mental arithmetic and just make, a silly mistake. Okay? So now comes the fun part. We are now in the normal distribution that has mean n times p. So guys, n in this case was 230. And p in this case is 0.63. So the mean is going to be 230 times 0.63. So the mean is 144.9. All right, so I'm going to go split screen here on you so we can see both things going on here. All right. Now we need to get the standard deviation. So the standard deviation is going to be the square root of n times p times 1 minus p. So the standard deviation is going to be n, which is 230, times p, which is the 0.63, times 1 minus p. I'm going to clean this up a little bit. 230 times 0.63 times 0.37. Now guys, we're going to want to run this out quite a few places. So I'm going to go square root of 230. Dogs are going crazy. I rarely get the video that the dogs don't go insane. All right, so I want to go out quite a few places here. So I'm going to go 7.3221. So I'm going to go out, always go out 4 places on a measurement like this. Now, what I've got here is I've got this normal distribution, mean of 144.9, and I am focusing on this continuity correction. Focusing on that interval. So I'm coming out here at x equal 150, which, again, guys, going back to the problem, that's the count. And I want to look at this interval from 149.5 to 150.5. This interval right here is important to me in these types of problems. Now, when I go back to the problem, I go back, what is the probability that more than 150 out of 238th graders? So what I've got to do is I've got to start at this 150, implement that continuity correction, and make my calculations based on the upper bound of the interval built around 150 to correct the fact that we have a discrete measurement, but we're using a distribution that is made for quantitative variables. We call it a ratio scale. Okay, so I have to run my probability from 150.5 all the way up to infinity. Guys, remember on our calculator, infinity up here, we're going to use E99. Now, if this problem came in here and said, what is the probability that less than 150 out of 230? Then I would have to focus on the lower bound of that interval and go from negative infinity, which we should know by now is negative E99, up to 149.5. Okay? So guys, on our calculator over here, we're going to go to distribution, normal CDF. Since we want upper, we're going to run this thing from 150.5 up to E99. With a mean of, I'm just going to type this in. And a standard deviation of the square root of 230 times 0.63 times 0.37. Close that up, go down here and go paste, and find our answer. So guys, our answer here would be 0.2222. Your online course management system, I'm pretty sure, will require you to enter these out to 4 places. Okay? Now, another way of doing this problem, and this is actually the way I like it. Now, I always hesitate to show multiple ways to do problems because the reason is because either way is going to work. But what students will do, sometimes they'll get clumsy and get careless, and they'll use a little bit of that one and a little bit of this one. Guys, that can run into major problems if you do that. But if you're consistent with what you do, this works fine. All right. Now, another way of doing this, let's get back to this problem right here, is to use a different distribution. And this distribution is still normal, but it has a mean of p and a standard deviation of the square root of p times 1 minus p over n. But this focuses not on x, but what we call p hat. And p hat is x over n. Now, it's a lot of notation. Your mind's probably getting ready to explode on you. Just chill, okay? It's going to be fine. I'm going to go through this, and we're going to see that instead of looking at all this and flipping out, we're just going to start with each particular number and try to figure out what that represents. Use what we already know about normal distributions to work the problem. So we've got a normal distribution. And what does this tell us? Mu is equal to p. What's this tell us? The standard deviation is the square root of p times 1 minus p, all divided by n. Notice every bit of this is under the square root. Not like some other stuff that we'll run into. This whole expression, entire expression, is affected by the square root. Focus isn't on x, but on p hat. So we need essentially 3 things. We need mu, we need sigma, and we need p hat. Okay, let's go back to our problem. Mu is the percentage that describes the population because it's p. In this problem, that's 0.63. The standard deviation is the square root of 0.63 times 1 minus that, all over n, which is our total sample size. Well, guys, we've sampled 230 8th graders. P hat is the count out of the whole that has the characteristic that we are measuring. We found out that 150 of these kids out of the 230, you can put this in our calculator. So I can call this about 0.65 of our sample. So about 65% of our sample, which is these 230 8th grade kids, have been exposed to drugs. All right. Guys, we still got to implement the correction. So we still got to implement the continuity correction. Which still focuses on the x out of 150. So we have a p hat lower which is 149.5 out of 230. And we have a p hat higher, which adds the 0.5 as we talked about earlier. out of the 230. Now, for the same logic that we have right back here, we look at the interval, but this time we're looking at the count out of the whole. So we're going to use 150 out of 0.5 because we're looking at greater than. So if we're looking at greater than, we use the upper end of the continuity correction interval. If we're looking at less than, we look at the lower bound where we subtracted 0.5 of the continuity correction. So guys, when we do this on our calculator, let's get this larger right here now because this is what we need. We're going to come into distribution, normal CDF. Now our lower bound is going to be what? It's going to be 150.5. Now a lot of students will stop there. Guys, no, don't stop. You've got to take that out of the 230 students that were sampled. Up to the E99. Guys, in this problem, the mean is 0.63. And the standard deviation is 0.63 times 0.37 divided by the total of 230. And close it up. Don't close it up too soon, because you want every bit of the p times 1 minus p divided by n underneath the square root. Paste it, hit enter, and you'll see that we get 0.222, the same as before.